The first lesson of this next unit is going to be on percent composition. And in this lesson, what we're going to look at are two things. We're going to look at percent composition by mass, and we're going to look at determining empirical formula. And so on to percent composition by mass. All right. When we have a formula, let's say that we have our old classic water, H2O. And so for water, so H2O right here, is that if we want to figure out what percent of this formula is hydrogen and what percent of this formula is oxygen, then there are two ways to do this. The first way is to look at basically what's called the mole fraction. And in the mole fraction, basically what we're looking at is we're looking at the mole ratio between the two. And so for this, what we'd notice is we'd say that we have two hydrogens and just one oxygen there. Can't see it because it's just implied. And so then we'd have a 2-to-1 ratio. That is, we'd have 66% hydrogen and 33.3% oxygen. The problem with this type of method is this is a great thing to use, and we use it as a mole ratio whenever we're converting between one atom to another atom. But the problem is that typically in most measurements that we're going to do of any molecule is we can't measure the number of moles directly. But, however, we can measure the mass. And so if we were going to react a certain amount of hydrogen, a certain amount of oxygen, we could measure the mass of that hydrogen, we could measure the mass of that oxygen before we reacted them. But it'd be very difficult to measure that number of moles. And so what we're going to be looking at in this section right here is not so much about the mass fraction or about the mole fraction. We're instead going to be looking at the mass fraction. The mass fraction, or the percent composition by mass, basically is a way of figuring out what mass of hydrogen we have total and then what mass of oxygen we have total. And so those are the things we're going to look at in this section here. So percent composition by mass. The way we basically figure this out is given right down here. Is said, let's assume that we have some chemical formula, and this chemical formula has the formula of element XX, A, YYB, and so like H2O, we have A atoms of XX, and we have B atoms of YY. So if we want to find the percent composition of XX, that is, what percent of XXAYYB that element XX makes up, here's our general formula, which we have sort of on the screen here. So, percent of XX is equal to A, that is the number of XX atoms, times the atomic mass of XX, times 100, and then all of that divided by the molecular mass of the whole thing, XXAYYB. So let's take a look at this in an example with the one we talked about before. So water. So water here we said formula is H2O. And so to do this, let's find what percent we have of hydrogen. So we're looking for percent of hydrogen here. All right. And so to do this, we first have to write down the first part. That's A right here, which is how many hydrogen atoms we have. Well, looking down here, we can see that we have a total of 2 hydrogen atoms. And so we go ahead and for this one, we'd put 2 in here. And then we're going to multiply that times the atomic mass of hydrogen. And so if we get out our periodic tables, we take a look at that. It says hydrogen has a mass of 1.01. Remember, we want to round to the hundredths place on this. And then times 100. That'll get it into percent right there. We're going to take this and we got to now divide it by the molecular mass. So we've got to figure out what the molecular mass of this is. If you remember from a little farther back that the molecular mass, the way we find that is we have to add up each of the pieces. So here we have, to find the molecular mass, we have 2 hydrogens. So times the mass of hydrogen is 1.01. And then we're going to add that to the number of oxygens. We only have 1 oxygen here. So 1 times the mass of oxygen. And look at our periodic table again. We see oxygen has a mass of 16.00. And so adding this up, 2 times 1.01 is 2.02. Plus 16 gives us a total mass of 18.02 grams per mole, like that. And so that means that whenever we're figuring out our percent composition by mass, that we're going to use for our molecular mass is 18.02. So we use 18.02 here. And so thus, to find the percentage of hydrogen in this guy right here, we'd say, get out your calculators. 2 times 1.01 times 100, and then divide that by the total molecular mass, 18.02. And by doing this, we should get, I made a mistake in my calculation here. So 2 times 1.01 times 100 divided by 18.02. I multiplied times last time. So we get from this the percent of hydrogen is equal to 11.2%. And so that means that water is 11.2% hydrogen. Now, of course, note if we want to define it for oxygen, we could do the same thing. For that one, we just take 1, that's what we get for our A, times the atomic mass of oxygen, which is 16, times 100, divided by the molecular mass of the whole thing, which is still 18.02. And let's take a wild guess what you'd get. Well, we know that the two percentages, since there are only two elements here, have to add up to 100. And so if the elements have to add up to 100, then that means that just sort of logically, if we wanted to find the percent of oxygen, it would have to be 100 minus the 11.2 that we got for hydrogen. And so 88.8 would be what we'd get if we did it that way. But both ways will work here. You can either calculate it out the way we did right here with this nice little percentage XX method here, or if you've already got all but one of the masses done, then you can basically just take 100 and subtract that off, and that'll get you the percent composition by mass. So, that being said, let's take a look at some examples and work out some test ones here. So, let's suppose this is the one we've got here. We've got Be3N2, and we've got to figure out the percent composition by mass of this. So, let's find for each of Be and for N. So, let's look first for our percent of Be. And so to do this, we have to take the number of Be's, and here that's going to be 3. So we say 3 times the mass of Be, that's beryllium. So once again, get out your periodic table. And beryllium has a mass of 9.01. So 9.01, then times 100 to get into percents. All this divided by the molecular mass of the whole thing. Well, we haven't figured that out yet, so let's do that here. So 3 times the molecular mass of the atomic mass of Be is 9.01, and then we're going to add that to the number of nitrogen, so that's 2. That should be a plus sign right there. That didn't pick that up very well, did it? Let's erase that. I erased more than I intended it to. Try this again. So we have 3 times 9.01 for the beryllium plus my marker just isn't even working right now. I'm not quite certain why. We'll say a plus like that. That's really strange. But plus, we have 2 nitrogens. So 2 nitrogens times the mass of nitrogen. You look on your periodic table, it's 14.01. So 14.01, if we add these two up, then you say, once again, get out the calculator here, 3 times 9.01 plus 2 times 14.01, and when you do that, you get 55.05. And so 55.05 is going to be our molecular mass of Be3N2, of beryllium nitride. And so that means we'll use that over here. So 55.05 is what we have here. So just some quick math here shows that we have 3 times 9.01 times 100, and then divide that by 55.05. And so we find the percentage by mass of Be has to be here a total of 49.1% Be for this particular substance right here. Now, just as a quick note, for the purposes of this class, is that we will be rounding our percent compositions to the 10th place. And so this actually is 49.1008, but we are going to round to the 10th place, so 49.1 is what we get for our mass of Be. And so let's take a look at our next one. Our next one would be nitrogen. And so to find nitrogen, what we do is, well, the simple way is simply say, well, if Be was 49.1, then the percentage of nitrogen would have to be 100 minus that. 100 minus 49.1 is just 50.9. So we have 50.9% nitrogen. Excuse me. So these are the two we get for beryllium and nitrogen. 49.1% Be, 50.9% nitrogen. Our next one here is tungsten persulfate, I think it is. No, tungsten sulfate, WSO43. And so let's just get the first step, let's get one of the steps out of the way. Let's find the molecular mass of this thing before we even start. And so to find the molecular mass, we know we have 1 tungsten, so we have 1 times the mass of tungsten. And so a quick look onto your periodic table tells you that tungsten has a mass of 183.84. 4, and then we're going to add that to sulfur. Well, we have 1 sulfur in the sulfate, but then we have 3 of those total, so a total of 3 sulfurs. 3 sulfurs times the mass of sulfur, which periodic table says is 32.07. And then our last one here is oxygens. It's SO4, but there are 3 SO4s. That makes for a total of 12 oxygens. So 12 times the mass of oxygen, which is 16.00. So add all these guys up right over here. And when we do that, let's take a calculator out. When we say 1 times 183.84 plus 3 times 32.07 plus 12 times 16, and we get 472.05. So 472.05, that's going to be our molecular mass for this guy right here. So let's find what the percent compositions are for these different guys. Let's say we're going to start off here with tungsten. And so if we want to find the percent tungsten, we're going to say, how many tungstens do we have? Just 1. So 1 times the molecular mass of tungsten, or the atomic mass of tungsten, which is 183.84. We already discussed that, times 100. And we're going to divide this by the total molecular mass, which is 472.05. 472.05. Okay? And so from that, if we do the math on this, we say 1 times 183.84 times 100, and then divide that by 472.05. And by doing that, we get 38.945. That'll round just to 38.9. And so we know we have 38.9% of tungsten. Our next one we want to do, let's take a look at sulfur. So we'll say percent of sulfur. And so to do sulfur, we say we have how many sulfurs? We have 3 here. And so 3 times the mass of sulfur, which is 32.07. 32.07, and then times 100 to get into percent. Okay, divided by the total mass, 472.05. And if we do the math on this, 3 times 32.07 times 100, and then divided by the total mass, 472.05. Doing that, we get 20.381. That'll round to 20.4. And so we have 20.4% of sulfur is what this compound is. Our very last one is our oxygen. And so to find percent oxygen, we could just add those 2 guys up we had before and subtract it for 100. But let's go through this one and use it as a double check. So we have 12 oxygens total, and oxygen has a mass of 16.00, and then times 100 to get it into percent again. Divided by the total mass, 472.05. So let's see what we get. We say 12 times 16 times 100, and then divide that by 472.05. And so when we do that, we get, excuse me again, 40.67. That would, that would just be 40.7. 40.7, that's a 4%. And so this is what we get. So we have 38.9% tungsten, 20.4% sulfur, and 40.7% oxygen. Our double check is, say, 40.7, the oxygen percent, plus the sulfur percent, which is 20.4, plus the plus the oxygen percent, the sulfur percent, 20.4, plus the tungsten percent, which is 38.9. And we add those up, we get exactly right at 100%. And so we know we've got this right. So this is how you go about finding percent composition by mass. Let's take a look at our next topic. Next topic is going to be on determining the empirical formula. Now, if you remember from what we talked about before, the empirical formula is the most reduced form of a chemical equation. If you have something like, say, hydrogen peroxide, if you look up hydrogen peroxide, you'll see peroxide is O2. It has a valence of -2. Hydrogen has a valence of +1. And so the overall formula for hydrogen peroxide is H2O2. However, that's a 2-to-2 ratio. If you were just looking at the ratio of hydrogens to oxygens, you'd see that that would just be OH. And so whenever we're working out something like this, an empirical formula is the most reduced form of a molecular formula. The empirical formula really doesn't describe anything physical. That isn't the number of molecules or atoms in each molecule there are. It's simply the ratio, or the most reduced ratio of atoms of one thing to atoms of a different thing. It turns out that what we can do, in the same way that we did before, we were able to take a molecular formula and find a percent composition. We can also take a percent composition, and then we can find an empirical formula. We can't find a molecular formula. We'll discuss that a little bit later, but what we can find is we can find this empirical formula. And the way we're going to do this is that to go from percent composition by mass to an empirical formula, we have to basically go to moles first. We're going to have to convert from percent into moles somehow, and then once we got moles, we can find a mole ratio, and that'll tell us how much we have here of each one. So probably the best way to do this is just by example. So let's say that we have a case where we have 69.6% oxygen and 30.4% nitrogen in a compound. Our first step has to be to convert to moles. The problem is that we don't have a conversion from percent to moles. But one of the nice things is that percents can be about any amount. You know, if I have 5% of, I can have 5% of 2 grams, I can have 5% of 10 grams, I can have 5% of 1,000 grams. That's fine. We get a choice of how much we want. And to keep our math simple, let's assume we'd simply have 100 grams of this stuff. And if we have 100 grams of this stuff, then by having 69.6% of oxygen, that's the same as basically saying that I have 69.6 grams of oxygen. And if I have 30.4% of nitrogen, the same as saying 30.4 grams of nitrogen. And so it's relatively quickly easy now at this point to convert. So, as we said, assume 100 grams of the compound, then we're going to convert each to moles. And so, if we look at our first one down here, that's our oxygen, then you see we start off with 69.6 grams of oxygen. To convert to moles, we have to divide it by the atomic mass. And so the atomic mass of oxygen is 16.00 grams per mole. And if we go and do that in the calculator, we find that we get 4.35 moles in 69.6 grams of oxygen. Similarly, we're going to go now to nitrogen. To find nitrogen, we say that we have 30.4 grams of nitrogen. And then we're going to take that and divide it by the atomic mass of nitrogen on your periodic table. You see that's 14.01 grams per mole. And we do that, we get 2.17 moles. Now, here's where the fun starts. In order to find the mole ratio, what you want to do is you want to divide each of the 2 moles by whichever one is smallest. Here we have 4.35 moles for one and 2.17 for the other. That means we're going to take both of these and we're going to divide them both by 2.17. And so divide these both by 2.17. One of these is easy. 2.17 divided by 2.17 is just 1. Now the other one, 4.35 divided by 2.17, if you go ahead and get your calculators and take them out, and you say 4.35 divided by 2.17, what we find is we get 2.0046, really close to 2. And so that means what we get here is a 2-to-1 ratio. And so we have a 2-to-1 ratio between these two. This is your mole ratio. If you have a mole ratio like this, you can then basically plug it in. We had 2 oxygens to every 1 nitrogen. So we have O2N if we just put it out this way. But the way we normally write things, remember, is we like to put the cation first. Oxygen has a valence that's only negative, and so it can't be the cation, it has to be the anion, so we're going to flip these 2 guys, and so that's why we go over here. And so we end up with the final answer on this one of simply NO2, because we have 1 nitrogen and 2 oxygens, with the cation being first. And so this would be the empirical formula for our 69.6% oxygen and 30.4% nitrogen. Let's try a few more examples of this. Suppose we have a particular chemical which is 48.2% iron, 41.4% oxygen, and 10.4% carbon. First step that we have to do here is we are going to divide each of them. We got to convert them to moles. And so if we convert them to moles, the first step is basically to say these aren't percents anymore, these are grams, right? So we get rid of those guys, we got grams in their place. And so we got grams of each one of these guys. And so with those grams, we can now go ahead and we're going to divide each one by their molecular mass, or by their atomic mass. And so if we take 48.2% of iron, let's look up what iron's atomic mass is. Atomic mass of iron is 55.85. 55.85. The atomic mass of oxygen is 16.00. The atomic mass of carbon is 12.01. So let's divide all of these. And so going ahead and breaking out the calculator, we say we have 48.2 of iron, grams of iron divided by 55.85. And so when we do this, we get the amount of iron, to be 0.863. And then for oxygen, we take 41.4, and we're going to divide that by 16, and we get 2.587. So we'll say that's 2.588. Okay. Then for our next one, we take 10.4 and divide it by 12.01. And for doing that, we get 0.866. Okay. And now remember, our last step is we're going to find whichever one of these is the smallest and divide all of them by that. And so the smallest one here is 0.863. And so let's divide each one of these by 0.863. So 0.863 divided by 0.863 tells us, this just gives us 1, so I know that I have just one Fe, like that. Then our next one is 2.588, so I take 2.588 and divide that by 0.863, and when I do that, I get 2.9988, that's basically 3. So I know I have 3 oxygens right here. My last one is 0.866 divided by 0.863. And when you do that, you get just barely slightly over 1. And so slightly over 1 is going to be just 1 here. And so that was just going to be a C. So my empirical formula here would be FeO3C. And a quick look at this would say, well, which one has to be the cation? The cation is going to be probably iron here. And so that one should be out front just like it is. And so we have Fe as our first one. The other two, O3 and C, we know these have to be part of a polyatomic ion. So if you look at your polyatomic ion sheet, do you see any that have carbon and oxygen in them? And just carbon and oxygen. And looking at this, there are, I was thinking there were 2 of them, but I only see one right now. Actually, there are 2 of them. There is oxalate, which is C2O4, and that doesn't make sense here. And the other one is carbonate, which is CO3, and that would work perfectly. Sorry about that. Took my headphones off for a second. So the next one has to be CO3. And so then we have CO3 for the rest of this here. And that makes it perfect. That's just iron carbonate. It's iron, let's see, what is that? Iron 2 carbonate. And so this would be what our empirical formula is for this first one here. Let's take a look at the next one. We have 69.9% iron and 30.1% oxygen. And so for this guy right here, basically what we're going to do is, let's say we're going to first basically convert these to grams. And so what we said was that these percentiles just go away. They both turn to grams here because we're taking this out of 100 grams. We want to divide both sides by, or both these two things, by their molecular mass, or by their atomic mass. So 69.9 divided by iron, which we said before is 55.85. So 55.85. And then we're going to do the next one by oxygen. Oxygen here is 16.00. And so we got that here. So let's do the math on those two. Quick little bit here says 69.9 divided by 55.85 gives us 1.252. So 1.252 for the iron. 30.1 divided by 16 gives us 1.881. And now we got to look and divide both of these two by whichever one's smallest. The smallest of these two is clearly going to be 1.252. So we divide 1.252 by 1.252, and we divide 1.881 by 1.252. And so the first one here just gives us 1. Now 1.881 divided by 1.252, and we do that, we get 1.50. Now 1.50 is not even real close to a whole number. This is a case, and this will happen sometimes, where that you'll end up with a fraction in one of your two answers, and it's going to be pretty close to basically a very common fraction. In this case, 1.5 is 1.5. And so 0.5 is a half here. Sometimes you want ones that are close to like 1.33 or 1.67. Those would be like the 1/3 and 2/3. Or you may end up with something that's like 0.2, which is 1/5. If that happens, what you have to do is you have to scale this up until you get a whole number ratio. Since this is a 1.5, we're going to have to multiply both of these by 2. And so if we multiply both of them by 2, then instead of a 1 to 1.5 ratio, this becomes instead a 2 to 3 ratio. And so that's basically what we're going to get here. And so if it's a 2 to 3 ratio, then we have Fe2O3 as our empirical formula. Fe, iron, is going to be our cation, and so that means that this is our final answer, Fe2O3 for the empirical formula here.